Hey everybody, welcome back to the last video lesson of this unit and possibly, depending on the timing of things, the last video lesson of the school year. Today we're going to talk about nuclear fusion. Nuclear fusion is the opposite of fission in that you take two small nuclei and combine them together to create one larger nucleus. And in the process, energy is given off in the form of heat. It's also given off in the form of gamma rays. Now, as a product, you also get some loose neutrons. Elements that are smaller than iron can be fused together. Iron is the largest nucleus that you can create through fusion. That also means that when it comes to fission, iron is the smallest nucleus that can be created through fission. There seems to be a stability of the nucleus of iron that makes it stand alone in all of the elements of the periodic table. So anything smaller than iron will fuse to make iron, and anything larger than iron will go through fission to make iron. Now, unlike fission, fusion is practically impossible on Earth. And because you need temperatures that are way too high and pressures that are way too high to attain on Earth in order to get two particles to come together and stick and become a new substance. So in order for this to happen, fusion pretty much only happens, in our case, on the sun or in the middle of stars. And so solar fusion is how we make elements like hydrogen atoms combining to make helium atoms. And then helium atoms can combine to make larger atoms after that, and larger atoms yet up to, as we talked about, iron. Now, I said fusion is nearly impossible, but it is in fact possible on Earth, but it's so labor and energy intensive that it's not actually practical in order to do. In other words, the amount of energy you put into a fusion reaction does not equal the amount of energy that is given off, and so, practically speaking, they're not useful. But there are some cutting-edge nuclear fusion reactors being researched as a possible energy source for the future. The advantage to fusion reactors over fission reactors is the fact that fission creates such terrible nuclear waste that is radioactive for many, many, many years, hundreds of thousands of years after the reaction has occurred. Whereas fusion reactors create simply bigger elements that are very safe in our atmosphere. Now, the one way fusion has been made useful, I guess, if you want to use that word for humans, is the fusion bomb, also known as the H-bomb. And in order for this to happen, once again, you need fusion, needs really, really high temperatures. And what they found is that if they can couple a fission bomb with a fusion bomb, the fission can produce enough energy to cause two nuclei to fuse together. And so you've basically got a fission-fusion bomb, also known as the H-bomb. But besides that, there really is no practical application for nuclear fusion at this time. The last thing we're going to talk about in this video lesson are called quarks. Now, back in the early 1800s, the smallest particle of matter that humans could imagine was the atom. And then in the early 1900s, we found things called protons, neutrons, and electrons. And throughout the 1900s, we tried to dig a little bit deeper into those subatomic particles. Those are the protons, neutrons, and electrons. Those are subatomic particles. And we asked ourselves, could we get any smaller than protons, neutrons, and electrons? And turns out you can. We call these subnuclear particles. And research has discovered 6 different types of things called quarks. Quarks are the building material for protons and neutrons. They come in 6 types. There's up and down, opposite of each other, charmed and strange, opposite of each other, and top and bottom, opposite of each other. A lot of research on quarks is relatively new in the scientific field. In fact, the last to be discovered is the top quark, and from my research, it has been discovered at or around 1995. Now, that seems like a distant past to us, but that's fairly recent in scientific terms. Of these 6 types, only up and down form stable quarks. The charmed, strange, top and bottom are created in particle accelerators. They are identified and then instantly turned back into energy, matter converted to energy, as we talked about previously. And so of these 6, up and down are the only ones that seem to stick around and are stable. So from that, we have interesting charges assigned to each up quark and down quark. An up quark is positive 2/3 charge, where a down quark is negative 1/3 charge. Now take a look at a neutron. A neutron is made up of 2 downs and 1 up. And if you add up the charges, well, you've got the 2 downs each at negative 1/3 charge, so that's negative 1/3 here and negative 1/3 there, and a positive 2/3 for this up quark. And if you add those up, they equal 0. Neutrons have no charge. This supports that. Take a look at the bottom picture. We've got protons. We've got 2 ups and 1 down. So the only difference between a proton and a neutron is a down turns to an up. Well, if you add up the charges, each up is 2/3 here and 2/3 here, and that equals 4/3 total. And then a down is negative 1/3, so when you add 4/3 minus 1/3, you get +1, which is the charge of a proton. So you can see how easy it is to switch from a neutron to a proton, which happens in beta decay. A neutron gets converted to a proton, simply by changing one of the quarks from a down to an up. The opposite can be done. A proton can be converted to a neutron, and that, in fact, is a different type of decay that we did not cover in this class, but we do cover in AP chemistry if you decide to take that next year. So it's pretty easy to convert from neutrons to protons. Just simply flip a quark. Well, that pretty much closes the book on nuclear chemistry, and that takes care of this video lesson. Thanks for watching.